I'm going to talk today about how to accelerate AI medical device streaming workflows with NVIDIA Holoscan, with an emphasis on workflows. I'm based here in London, UK. My job involves supporting various companies, partners, academics with the use of our hardware and NVIDIA. So let's kick this off. There's a strong interest in software-defined medical devices. Devices could be scanners, they could be endoscopy, laparoscopy, so surgical robots, and through the software-defined paradigm, you can quite easily integrate AI, which is very interesting to many these days. For example, various decision support, assistance during robotic procedures, defining no-fly zones, and AR, reality, etc. So there's basically a massive interest in these applications and adding them into pre-existing devices or new devices to be developed. And the examples, for example, of these type of workflows, so two, one academic and one from a big medical device manufacturer. One is from Orsi Academy in Belgium, that basically is a training center for surgeons, where they can play around with different systems. This is a laparoscopic surgery with AI augmentation. And on the other side is a device from Medtronic that recently got FDA clearance. And a little bit more in detail. So Orsi, they had this application where they use they have a Da Vinci, and they grab video feed, and during a procedure, in this case it's a stent, shifted, it's an emergency operation is needed, so they built an application that takes a peripheral CT, segments it, and then documents in real time during the procedure the location of the stent and also the artery, and also segments all the tools in the video feed so that the 3D model ends up below tools. And usually workflows like this can be thought of as kind of like a graph where you have some source of data, some pre-processing, some AI inference, some post-processing, some visualization. Medtronic have a quite similar application. It's part of the Genius platform. This was FDA cleared not that long ago. It's used for colonoscopy, polyp detection, and the actual application is quite similar, reading or taking in sensor data, doing various type of processing, AI inference, and visualization. A cool thing about the Genius platform is that Medtronic also allows for ICs, independent software vendors, to deploy their own software on this platform. So there are, for example, companies that develop applications for example, whilst you're doing a colonoscopy, making sure that you have actually examined the entire colon by kind of reconstructing a 3D model whilst you do the procedure. So there are both of these platforms have their challenges if you want to implement them. There could, for example, be very high requirements on the bandwidth and throughput. So you want to run this on very high resolution images or very high frame rates, or you want to do multi-animals in parallel. There could be a need for edge to cloud scalability. Maybe you want to deploy some compute on an edge node. Maybe you would want to pass data from that node to a more powerful data center compute. You want to have easy access to building in AI scalability. And also, what was touched on earlier, you want to have production readiness, medical grade, long-term support, which I guess was one of the challenges that we mentioned early on. And that's sort of where Holoscan comes in. So Holoscan is essentially a platform, and the part of the platform is open source. I'll get into that soon. But overall, it's a platform to enable building applications that takes in some type of sensor data, it could be video data, it could be radio data, whatever data you're getting in real time. Importantly, this data can be of extreme large bandwidth requirements using some of these clever networking hardware that's in our data center hardware that NVIDIA has is available in this platform. There are a bunch of models, and there's also a way of developing applications. This platform runs on various hardware. So Jetson is NVIDIA's embedded product line with ARM64 instruction set. It runs on x86 workstations with eGPUs up to large DGXs, where you might have heard like large language models being trained. And interestingly, is that the applications we previously saw were all developed with the Holoscan platform. So Orsay's work, and just like Mikael said, we collaborate with a lot of academics that do state-of-the-art research. They are running it on Holoscan. Medtronic's AI Genius is entirely built on Holoscan. FDA cleared. Moon Surgical, I don't know if you've heard of them. They have the Maestro system, also got FDA cleared quite recently. And then you might think that, okay, this is maybe it sounds great, but it's actually quite complicated to go from here's some sort of platform to getting an FDA clearance, and that's where the connection to a hardware platform comes in. So Holoscan is part an SDK, but it's also hardware, and that's called IGX. So just like many other product names at NVIDIA, DGX, for example, we have IGX. IGX 500 is based on the Jetson AGX. IGX 700 is a more advanced platform that has this networking interface code allowing 200 gigabit per second network streaming directly to the GPU memory. There's two GPUs actually. There's one on the Jetson and one on this workstation discrete GPU. And with this platform, you can get, as I said, very low latency. Also, full stack long-term support on software. So the entire NVIDIA software stack is supported by NVIDIA. This runs Linux operating system Ubuntu. So Canonical is used as providing support for that software component. I guess the video is kind of showing, but the software and hardware is the three certification for both software and hardware, 6204, 6201. So what happens is we use OEMs. So an OEM would pick up this platform and then build some box and then take it to actual production readiness. And we provide documentation to fast track this, like release notes, like a lot of the things that was discussed earlier. So, but in the end, NVIDIA will not do this clearance, but simplify it. And proof of that working in practice is that there are like the compute units. So I've kind of talked a little bit about the Holoscan platform, and you can think of like developing these kind of applications having 5 steps. And if you want to involve an AI model, then you would want to train that. You could use something like Monai or whatever library you would want. And then you want to build your streaming application. This is where the Holoscan SDK comes in. And then you will test and validate. So we have dev kits. So this is where you can prototype your application. And then when you would deploy scale, you use an OEM to build your own form factor hardware. And then we support maintenance and upgrade to something called NVIDIA AI Enterprise. But since this is about open source software, so that Holoscan does not involve training AI models. It involves these 4 components. But I'm going to focus on the open source part of it, which in practice does not require to buy any fancy expensive hardware. As I said, this could be run on some x86 workstation or a cheap Jetson. Requires an NVIDIA GPU, whether it's an integrated or discrete one. So let's dive into Holoscan SDK. So it's an open source software from GitHub. I think been on GitHub for a little over a year, maybe. It has around 50,000 downloads at the moment. It's not like Monai, a work that other companies or universities have been involved in is purely developed by NVIDIA, which means that our engineers have made sure that it has a very optimized implementation for building these streaming applications in terms of how data is passed, not making sure that unnecessary copies are being done, who that's utilized in an optimal way. There are C++ and Python APIs, has x86 support, but also ARM64 support. It builds on both platforms. That's because all the JETSON embedded hardware uses ARM64. And there's also, as I will mention soon, global sample applications. Performance is like really the key here. So the SDK is more like you can say that if you have something that runs okay, but it's not good enough at the moment to maybe deploy in real time because of software or hardware issues, this might be the SDK to use because it has a lot of nice tweaks to the implementation. And yeah, the production readiness is very important from some companies' point of view who want to take all the way to a product in the long-term support. I'm not going to go into details about this bit. There's bunch and bunch of information online. I'm going to talk a little bit more about the SDK itself and how you can implement applications. So these are, now I'm diving into a few details here. So whenever you see one of these applications where there's data ingested, there's some processing being done, and then there's maybe some visualization of data being this could be passed somewhere else. It can be conceptualized as kind of a graph. It could be directed acyclic, or it could have cycles. It doesn't really matter. This is sort of DAG in Holoscan lingo, the SDK that I've been telling you about. We have operators. So operators, they're basically, they take as input, they have input ports, they take messages, they do some processing, and they pass the messages onwards through output ports. And then, you know, based on that, you can build whatever kind of graph you would want. And then when you run your application, it basically just executes the graph you see here. So let's say this is a camera. This operator has been linked to some camera driver. It basically takes data as input over HDMI, SDI, or Ethernet, and then it passes that onward to some post-processing, passes it onward to some AI, passes it on to some visualizer. That's literally it. That in the end becomes an application. But these can be built to very complex forms, and the different types of schedulers. You can run them in an agreed way or multi-threaded, etc. But the main thing to remember here is that an application is literally a graph. The graph has nodes. Each node is an operator. The edges are just messages being passed along each node, and then there are ports and also various conditions for when this operator should run and this operator shouldn't, and so on. So you can make almost arbitrary complex graphs using this SDK. And as I said, it's implemented in C++ and CUDA, but each C++ method has Python binding, and that is something that we see a lot. It's popular option to use for development. So the operators, well, you can build your custom one, but there's also a bunch of them already available. These are contributed by NVIDIA, but we also have third-party contributors, which this could be, for example, a capture card manufacturer who would want to make the capture card by AJ or whatever available, and maybe they would contribute an operator to make it easy for a user to use that particular hardware with the Holoscan SDK. So for I/O, for example, well, we have read-for-all 2 operators that you can use to take in various video data, for example, over webcams, or maybe camera supports the read-for-all 2 API. AGA, as I said, DDS, the middleware for publishing, subscribing data between various devices, streaming video from disk, of course. For computer, various format converters. The inference operator is very advanced, so it supports, or it builds on the TensorRT, NVIDIA's TensorRT SDK, which is an inference accelerator. Does a lot of clever tricks to a pre-existing network to make it run much faster. So here you can literally just point this to an omics model that you might have exported from PyTorch. It will automatically build this into a TensorRT engine and considerably increase the inference time decrease. There's also segmentation post-processors. I don't know if you heard about CUDA. It's like an option to OpenCV that is purely written in CUDA that has a growing number of features almost every month. This is also open source and contributed to by NVIDIA. I think it's very popular if you look at the number of stars on GitHub. MPP is also NVIDIA performance primitives that runs on Jetson for doing various image processing. Visualization is the Holovis reviewer, and that is written with Vulkan. And it has a nice feature of being able to render onto the screen from a GPU buffer. So this means that what you can do with Holoscan and one of these IDX platforms, you can take data onto the device, pass it directly into GPU memory, do all your compute and your rendering, never leaving GPU, not having CPU involved at all. And that's what enables very performant applications. QT, mentioned earlier, and WebRTC, well, maybe some of you are familiar with some of the drivers. And there's also the HoloHub. This is a separate GitHub repository where there are sample applications and sample operators contributed. So here you can find sample applications for endoscopy, out-of-body detection, multi-AI inference, ultrasound, but also non-healthcare related. Because this SDK is not healthcare specific. There are requirements on large data being taken from some sensor also in things like astronomy, particle physics, or other applications. So yeah, let's quickly just run through a HoloHub sample application. So if you go to the GitHub page of HoloHub, you can find the endoscopy tool tracking application. So basically just tracks tips. So here, this is, as I said, simple graphic operators. In this case, you read data from this, you do the format conversion, you run some LSTM model with TensorRT, and then you do some post-processing. It's visualized in the viewer that's part of Holoscan, both the video and the output from the inference model, and then it's all recorded. So these are all operators that are in the SDK. But as I said, it's quite easy to write your own operators. So you can literally in C++ link to whatever library you would want, or likewise in Python, have some package and just build your custom operator. This, by the way, it runs as a container, so it's all Docker to make sure that all dependencies are easily available. So this is a high level, almost pseudocode run through what an application is like. So it is Python, but not everything is here. Otherwise, it will be a bit messy. So if you go to the actual GitHub link, there'll be more comments so on. But basically, the application is a Holoscan object that you import from Holoscan's Python installation. You can then define a class that inherits from that application called, in this case, endoscopy app. It has a compose method. I'm going to go into detail about that soon. But the main method basically just instantiates this endoscopy app, reads some parameters, some options from a config YAML file, but it can also be done in a different way, and then you run the app. So this is like, very, very high level, but should give you like just an idea of how easy it is to write one of these applications. And then the compose method is basically just instantiating these different operators, right? So we have this one has been imported from Holoscan, the Python package. So this is the source. This could be some other capture card or whatever. So you could just plug this one, plug and play with whatever other source of data you have. And then this format converter that might go from uint to float. And there's also recording the data. And there might be two format converters here because you want to convert the video data before it's visualized, but also the data before it goes into the network. The LSTM inference, interesting to see here, is that you give it this model file path, so that's the omics model, and you build that into the TensorRT engine. The CUDA stream tools, I don't know if you know what CUDA streams are, but that is ensuring that the implementation on the CUDA level is efficient. So there's like a lot of CUDA tweaks in here. And yeah, in the end, this is the visualizer that does the rendering using Vulkan direct from the GPU. And it also actually passes onwards after rendering it to screen. It also passes the blended video and the results from there. So simple app, this decompose, creating different operators. Then lower down in the same function is just building the flow. So this is where you have each operator and you link and you build the edges. So you will say like, okay, so the source connects to the formal converter, and then you have defined certain names for those messages. So it's quite simple. And like I said, you can build much more complex applications than what's shown here. But the idea is to just give you kind of an idea. So that's really it. And then these operators can also be custom. So you can write them. The idea is that, oh, maybe you have something that you will made useful in various applications. Is maybe a particular operator reading camera data may be useful not only in one application, but across many. So that's the plug and play aspect of it. And then quickly, a cool feature and one of the selling points is that you can create these operators, collections of operators as fragments, and you can run these fragments on different nodes. So you can have one running on like an IGX or a Jetson or workstation, some particular application. Say, you have a photon counting CT scanner that reads data as huge amounts. You can pass that data then very efficiently with some fiber Ethernet to, let's say, a DGA, so some compute server that's very powerful, and do some image reconstruction, and then maybe pass it over somewhere else. So this and the API is very transparent. So you code up your application with these different operators, and then they can just run transparently on one device or multiple devices, and that's part of the SDK. And there's a lot of nice features about it, making sure that again there's no unnecessary copies, and this builds on something called UCX, Unified Communications Library. So that's the sort of protocol that is used underneath for sending the data. It literally involves kind of like defining IP addresses, and then the data can be passed between different nodes. And this is very well documented, because if we want to support or make companies easy to pick this up and bring it all the way to a FPGA device, no documentation must be good. But then I know that, for example, Joe, who works at Cambridge Consultants, might not agree that the documentation is spot on yet. They work a little bit with this, but we're getting there, hopefully. So yeah, there's loads of more info, and there's also sample application of this. So talking about Cambridge Consultants, so actually, maybe you didn't notice it, but the demos that was shown during Hammer Symposium, two of them actually used Holoscan SDK and this IGX dev kit. So it was the demo by Cambridge Consultants, where they ran a bunch of different AI models to, among other things, have a super resolution of surgical video. So here you see the IGX Orin box that runs Holoscan SDK. And also on the right, we have RTI, represented by Darren in the back. That did another application. You have also an IGX Orin here, where they use PDFs to pass data in between the IGX Orin, a laptop, I think a Raspberry Pi, and the AI inference was running on the IGX Orin. So yeah, so why Holoscan SDK? So yeah, I'd say the API is quite intuitive, and it runs Python and C++. You can run those x86 and 164. You wouldn't have to buy it, get some or the IGX hardware. You can buy it on your laptop, the workstation, built for efficient data ingestion passing. You can write distributed applications. This might be more of a part of the possible rather than like, oh, this is what you should do with this. It's more like, oh, maybe this could be an interesting use case. There's efficient operators and sample applications already available. You can create your own. Long-term support and simplified clearance. I haven't gone into details here because this is a lot of info. And it allows for building these low latency and high bandwidth applications that might not have been possible unless you would use a VPU a very efficient way. And yeah, you can get started. Basically, it's built from source, from the code on GitHub. You can pull it from NVIDIA's and NGC container repository, pip install it, or apt install it to the Debian package. And it's really not that complicated. So if you want to get started with a they supported NVIDIA GPU, which are most of them. You use clone HoloHub, you seed into the folder. It's all using containers, and there's build scripts, so you can just build in this pulse the Holoscan SDK container. You then launch HoloHub, and you can pick whatever sample application you want. Let's try it. Goes to the tool tracking, and then just build that, and then you can run either the CPP or the Python version of it on a supported system. And in the end, you will have something like this popping up promptly on your monitor. And yeah, that's it. So a lot of content. I guess I spoke quite quickly, but hopefully you got an idea of what Holoscan is. So thank you very much.